This is a video of the worked solutions for the P1 Cambridge International exam, and it's the paper variant 12 from the March 2018 season. So we've got a curve, a point on the curve, and the function that gives the gradient. So if we integrate that function, we'll get back to the equation of the line. And for integrating, we need to raise the power by 1 and divide by the new power. And then we've got plus c. So y equals that equation. And when when x equals 4, y is minus 6. So minus 6 is equal to 4 to the half times 2 minus 3 times 4 plus c. So from there we can work out c. And then put it all into the final equation of the curve. Question 2 is about binomial expansion, and you have the formula for this on your formula sheet. So using the formula goes like this, and we just need to go far enough so that we can get the powers of x that we're looking for, and that's x squared and x to the power of 3. So we'll just go as far as we need. So this one here will give us the squared term, and our next one will give us the x cubed term. One thing to be careful of is to make sure that you take that minus 2x as the whole thing that goes into the bracket. In these parts here, it needs to have that minus in it as well. Okay, so now picking out the parts that we need for the x squared will be this section here. So if we expand that, well, 7c2 is 21, and then from the minus 2 squared, we'll be multiplying that by 4. So the coefficient of x squared is 84. And then for the x cubed, we're looking at this portion here. So 7c3 is 35. And we'll multiply that by the minus 8 that we get from the minus 2 cubed. And we get a coefficient for x cubed of being minus 280. So part 2 is looking for the coefficient of x cubed if we take that expansion that we just did in part 1 and multiply it by 2 plus 5x. So the pieces that we needed from the previous expansion are to do with the x squared and the x cubed part. Now, if we do 84x squared multiplied by 5x from doing this bracket times by the x squared portion of this bracket, that will give us x cubed. And that comes to 420x cubed. Then if we do a similar thing, but we're taking the constant from this bracket, the 2, multiplied by the x cubed part of the second bracket, the expansion, so times it by the 280 x cubed, that will also give us an x cubed term. And that'll be minus 560 x cubed. So then the coefficient of x cubed in that full expansion from the top will be 420 plus minus 560. So our final coefficient for x cubed is minus 140. Okay, so just take a minute to read this question. And then model A is going to be an equation like this. So if we call the height y and x is the number of days, then if it's growing at the same rate as on the first day, it's growing 1.2 per day, and it had a starting point of 40. So this is the equation we're going to use for part I. So the height after 60 days will be 1.2 multiplied by 60, add on 40, which is 112 centimeters. Now model B is using the rate of growth rather than that linear model we looked at just before. So this is, we need to work out what that rate is first of all. So if you do 1.2 out of the 40, It's growing that 1.2 on the first day, having started from 40. That gives us a percentage change of 3% increase per day. So if we turn that into an equation, y being the height of our plant, it'll be 40 times by 1.03. So that's if we want to increase something by 3%, we times it by 1.03, and then we'll do that to the power of how many days we've got. Well, on the previous slide I called it x, so we'll stick with the x there. Okay, so now if the number of days is 60, we can put the 60 into there, and that will come to 236 centimetres. So we're going to start by drawing a picture of what we're being told in question 4. Once we've got that picture, it's pretty easy to spot the basic trigonometry that we've got going on. So this is a length of 2. We've got an angle of pi by 6. We'll be using tan to work this out. So OA is equal to 2 over tan pi by 6. Now tan is one of your special values, and we've been told specifically to give an exact value from the question, so do not go decimals at this point. You have to do 2 divided by, and tan of pi by 6 is 1 over root 3. So OA equals 2 root 3. So the x-coordinate of A would be 2 root 3. So now we need to find the perpendicular bisector. We'll start by finding the midpoint of the line. So that's halfway between A and B. So halfway along in the x direction will be root 3, halfway in the y direction will be 1. Next we want the gradient of the line, which is rise over run. We're coming down on the rise, so it's a minus 2 over 2 root 3. So the gradient is negative 1 over root 3, making the gradient of the perpendicular the negative reciprocal, so that's root 3. Use our equation of a line, substitute in our values, so the y value is 1, the gradient is root 3, the x1 value is root 3. Then expand that out, so we get root 3, root 3 times by root 3 is just 3, so we get a minus 3, and then add the 1, so we've got minus 2. So first up we need to rearrange this equation into a quadratic. So multiply through by the denominator first and expand that bracket. Next, a little bit of rearranging just to tidy things up. And then factorize, so we can solve this into 2 brackets. As follows, that's going to need a plus 2 here and a minus 1 there. So then solving this, we get tan x is equal to a half, or tan x is equal to minus 2. Don't forget to have your calculator in radians because our range is from 0 to pi. And these are not nice exact values, so we will have decimals this time. We'll have a 0.464 and 2.03. So this one is all about knowing your graphs and how they can be transformed. So if we start off with a regular graph, so this would be if it was just sine theta, and it would go between 1 and minus 1, and it would cross at 180 and 360. And then we want to compare the equation that we've got here and use the properties of transformations to see how we can make the graph that we've got below it. So the k is all about a stretch. We've got a multiplier there, it will stretch the graph, and this one will go in the y direction. Inside of the function, we've got an addition of alpha. This will be a shift. If we're adding or subtracting something, it's a shift, and because it's inside the function, it will be in the x direction. Now that's the easiest one to think about. We can see we've got a shift from 180, where it was on the original graph over here. It's now at 150, so it's got a shift to the left by 30. So that alpha has got to be 30 degrees. Now for the k, we haven't actually got the maximum or minimum labelled here, but we have got where it goes through the x-axis, so that we know that when, the y-axis, when theta equals 0, y is equal to 2. So we can pop that into our equation. So replacing theta with 0 and y with 2, and then we can work that through to work out what k needs to be. Well, sine of 30 is a half, so 2 is equal to a half k, therefore k must be 4. With question 6, we've got two overlapping sectors of circles. So we're told that PO is the radius of the white circle, the POQ circle. So this is also 10 centimeters over here on this side. OQ must also be 10 centimeters because it's the radius of that circle at center 0. And we want to work out PQ. So we're going to use the cosine rule for that. And that comes to 317.7. So PQ is the square root of that, which equals 17.8 centimeters. Okay, so just copying over the diagram with the information that we know about it, now we want the perimeter of the shaded region. Well, we know that this section here is a sector of a circle with center at P. So PR is equal to 17.8 as well as it being PQ. We work out QR by being the length of the arc there. Now to work out that arc length, we need the angle RPQ. Now that angle is going to be equal to pi minus 2.2 over 2, because we've got that isosceles triangle POQ. The angles in a triangle have to add up to 180, which is pi in radians. So take away the 2.2 that's already there, divide it by 2 to get what would be equivalent to these two angles here. They would be the same. Now the arc length for RQ is r theta. So this will be, the radius is 17.8 times by pi minus 2.2 over 2, which comes to 8.38 centimeters. So the perimeter that we're looking for on the shaded region will be that 8.38 plus the 10 centimeters of OQ plus for the OR, that will be the 17.8 minus 10. Giving us our final answer of 26.2 centimeters. Question 7 is our vector question. You're going to need to take a minute to stop and read through and understand the diagram and what it's telling us. So first of all, we need to work out the vector CE. So think it through in logical steps of how to get from C to E. So if we start at C, we've got to go in the I direction, but in the negative I direction by a distance of 4. So we've got negative 4I, because it's this distance here from C back to the corner of that rectangle. Then we need to come along in the J direction. This one is also negative, so we're getting from the corner of the rectangle, still kind of on the bottom of that plane, but from the corner of the rectangle to D and we're going by 1 in the negative direction of J, so we get a minus J added to our root, and then we need to go up 8 to get from D to E. We're going to move up by 8, so we're going to go 8 in the K direction, so we get a plus 8K. Then the length of that is fairly straightforward. We're finding the modulus of that vector, which will be the square root of minus 4 squared plus minus 1 squared plus 8 squared. And that comes to 9. For part 2, we're looking for the angle ECA, which is just here, and it's between these two lines here from CE and CA. So we're looking for the angle between the vectors CE and CA. Well, we've just worked out CE, so now we just need to work out CA and then use scalar product on them. So for CA, if we're getting from C to A, we need to go along from C to B first. So that is in the I direction, so that's a 3I. And then from B to A is to come in the negative J direction by 3, so minus 3J, and we're not going up at all. So it's nothing after that. You could put a plus 0K if you want to, doesn't really matter. And then we'll go on and use the scalar product to find the angle between. So our formula for scalar product looks like this. So we're going to need the modulus for CA as well as just the vector of it. So the modulus of CA is the square root of 3 squared plus 3 squared plus 0 squared, but we're not going to bother to write that. And that will give us the square root of 18. So then cos theta will be the scalar product of those two vectors, which is minus 4 times 3 plus minus 1 times 3 plus 8 times 0 over 9 times root 18. That becomes minus 9 over 9 root 18, or minus 1 over root 18. So theta is the inverse cos of minus 1 over root 18. So putting it into the form they've asked for in the question, m is 1, n is 18. No, it's not. M is minus 1. Hold on. There we go. It's now in the form that it wants it to be. For coordinates of stationary points, we need to find dy by dx and set it equal to 0. So if we differentiate, we get this. Set it equal to 0, we get this. Now we actually have here a coded quadratic to try to solve. So if we rewrite this as a being x to the half, you can see that quadratic a little more easily. Now we can have a go at factorising it. That becomes minus 4 and a minus 2. So a equals 4, a equals 2. So x to the half equals 4, or x to the half equals 2. And just remember, x to the half simply means the square root of. So the square root of x is equal to 4 and 2, so therefore x is equal to 16 and 4. For part 2, we have already got dy by dx from the previous question, so we just need to differentiate a second time to get d2y dx squared. So we get 1 minus 3x minus half. Now from our previous two parts, we know that the stationary points happen when x is 16 and 4, and that d2y dx squared is equal to 1 minus 3x minus half. So when x is 4, d2y dx squared equals minus half. If you just substitute that in, that is less than 0, therefore that point is a minimum. So whoops, wrong way around, that one is a maximum. Same again when x equals 16, d2y dx squared is a quarter, that is bigger than 0, therefore that one is a minimum. If those lines are going to meet, there's going to be a point of intersection. So 1 over x plus c will be equal to cx minus 3 at some point. So we can work that through and figure out what c has to be to make that work. So if we multiply everything through by x, we'll get 1 plus cx is equal to cx squared minus 3x. Rearrange that into a quadratic that's a little bit easier to take a look at. So we'll have cx squared minus cx minus 3x minus 1 will equal 0. Now for this quadratic to be solvable and there to be a solution, we need b squared minus 4ac from our equation for the discriminant to be greater than or equal to 0. So from this quadratic, b is the coefficient of the x term, so that's minus c minus 3 squared minus 4 times a, which is c, confusingly enough, and c, which is minus 1. That's got to be greater than or equal to 0. We get down to another quadratic, but it's a quadratic inequality that we need to look at. Now if we factorize this, we'll get c plus 9 and c plus 1 has got to be greater than or equal to 0. So we know our critical values are minus 9 and minus 1. If we draw a little sketch of the quadratic, it's got to go through minus 9 and minus 1 like this. That's pretty bad drawing, but it's close enough to know what we need to do. And we want to know when that will be greater than or equal to 0. So it'll be these portions here when it comes above the x-axis. So our final inequality is that c has got to be less than or equal to minus 9. So it's got to go that side of minus 9, and it needs to go that side of 1. So c will be greater than or equal to minus 1. Okay, so we know that the tangent will happen when those lines just touch but not actually cross. That will be at the limits that we just found on the other one. So c has got to be equal to minus 1 or minus 9 to make tangents. So that the straight line equation that we've got will be a tangent to the curve. So from there we then need to find out where that happens. And remember that we had this equation before for the point of intersection. So when c is equal to minus 1, we will get minus x squared minus 2x minus 1 will be equal to 0. Or x squared plus 2x plus 1 equals 0. Factorize that and we get x plus 1, x plus 1. So x equals minus 1. Then when c equals minus 9, our point of intersection becomes minus 9x squared plus 6x minus 1 equals 0. Which factorizes to 3x minus 1 squared, so x becomes a third. Our function question starts off with some straightforward 1-mark questions. So the range of the function f, well, take a look at the domain for f, which is x has got to be bigger than 2. So the bottom of that function there, the smallest that can be is something just above 0. So then the limit is that value of something that's very, very small plus 2. So then we get that f of x has got to be greater than 2. Now that portion there at the beginning of f cannot be equal to 0. So we don't get a greater than or equal to 2 on our range. It'll be strictly greater than. Now for g of x, we actually have a limit here on the top of the domain of the biggest that x could be is 4. So if we think about what happens when we put a 4 into this equation, we'll have 8 divided by 4 minus 2. So that's 8 divided by 2 is 4, and add on the 2, so that'll be a 6. If we go down to the 2 part of that equation, then what we're doing is getting close to having the bottom of this fraction then being very close to 0. So close to 0 there. Now if we do 8 divided by something very close to 0, we're going to get a large number. So 8 divided by a big number and then add on 2 is still a very, very big number. In fact, we can do anything, any size number, as long as, you know, we're going up to infinity on that one. So the smallest that could be comes from the 4. So therefore, g of x can be anything from 6 upwards, because if we put in the 4, we get the 6, and we can put in anything else after that to make something that's bigger than 6. Now in part C, if we're doing the function fg of x, it means we do g first, and then we put what comes out of that into f. So we know that what can come out of g is that g of x has to be greater than 6. That becomes the domain for going into f of x. So if we put that limit of 6 into f of x, if you do 8 over 6 minus 2 plus 2, you'll get a 4. So that's going to give us one limit on what can come out of f of g. Now, if the things going into f can be anything above 6, then think what that could go up to. So if you did 8 over 10 minus 2 plus 2, or 8 over 100 minus 2 plus 2, you're going to get 8 over something very big, which makes that fraction become very small, and then you always add 2 to it. So the fraction part of it is going to tend towards 0, and then you add on 2. So the bottom limit will be a 2 for this range. So our range for f of g can be anywhere between 2 and 4. Okay, now part 2, if we think about it the other way around, so if we're doing g of f, we're taking what could come out of f, which we already know was that f of x has got to be greater than 2, and we're putting it into g. So doing f first and then entering that as our domain for g. Now that range of f doesn't match up with the domain of g, so we can't do that g of f function because it's not defined for anything outside of that range. So the range of f extends beyond the domain of g. We're trying to put things into g that aren't allowed to go in there. So we've got a few things to work out on this before we can go ahead with solving it. So the first one is to work out f dash of x, which is to differentiate f of x. And I'm just going to rewrite that in a way that's easier to see the differentiation on it. So this becomes minus 8x minus 2 to the minus 2. Then the inverse function of f of x, we need to work out what that will be. So if we write y equals 8 over x minus 2 plus 2, switch over the x and the y and then rearrange it so that we have y as the subject again. So you can pause and have a read through that rearranging if you want to, but the end result is that f minus 1 of x is 8 over x minus 2 plus 2. Now I'll just clear that out of the way so we can carry on. So we've got 6 f dash of x plus 2 f inverse of x minus 5 has got to be greater than 0. So substituting in, we get this. And then we need to do quite a bit of tidying up. And then I'm going to use coded quadratics to try and sort that out. So let a be x minus 2 to the minus 1, and we get a quadratic in a. So then a will be 1/12, or a will be 1/4, and then solve. So we get down to the critical values of x being 14 and 16, but we need to go back to the fact that this was a less than 0, so we need this as an inequality. So our quadratic was a negative quadratic, so it's an upside down parabola, and it's got the critical values at 6 and 14, and we want to know when it goes below 0, so when it's going below the axis here and here, so it needs to be above 14 and below 6. So x would be greater than 14 and x is less than 6. Now there's one very last step that I imagine a lot of people didn't think about, which is this range of values that we have that can go into the domain of these. So we're actually limited on what x can be. So I shouldn't have circled the g. We're actually only interested in the f1 for this question. X has got to also be bigger than 2. So it can't just simply be less than 6. We've got a limit on what it can be. It can go between 2 and 6. So less than 6, but it's stopped by that 2. It can't go below 2. That's your final answer there for the set of values of x that can satisfy that inequality. Okay, so we've got this curve. We want to show that AB is a tangent to the curve. We are told that AB has an intersection at the point A. So if we do dy by dx, then we get -2, and then we're doing the chain rule on this part here. So we'll do that and then times it by, oops, that should have been a 2 there, and then times it by the -2. So that becomes -2 plus 6, 1 minus 2x squared. So at the point where they intersect, x is equal to a half. So if we pop a half into dy by dx, we get that the gradient is equal to -2. The gradient of AB from the equation of the line is also -2. Therefore, AB is a tangent. Okay, so to find the area, if we want to find the area under the curve, we can integrate. So we will be integrating between 0 and a half for the point from the origin up to that point where they cross at A. And we'll do it for the top line, so the 1 minus 2x, and then we'll integrate from 0 to a half and subtract it from the other one of the curve, which is 1 minus 2x minus 1 minus 2x cubed dx. And we can combine them into one integration, which you can see then simplifies down to simply being the 1 minus 2x cubed. So for part 3, we integrate using the reverse chain rule. So the integral becomes 1 minus 2x to the power of 4, and then divide it by -2. And we're going to do that between 0 and a half, which if we put a half into there, we get 0, and take away, if we put a 0 into there, we get minus a half. But I'm going to need to backtrack because I have realized a mistake. Back in our integration, this should have been divided by 8, because we needed to divide by both the new power of 4 and the derivative of the inside, that -2, so it becomes -8. So anyway, back to where we were. If we put in a half, we get the 0, and then if we put in a 0, we get -1/8. So our area becomes 1/8.